Welcome to Lecture 9. This lecture will give you an introduction to enzymatic processing. There are a few base definitions that you will need to know with respect to energy transfer in the cell. First of all, energy is simply defined as the ability to do work. There are different types of energy that you can have. However, for the purposes of this course, we're going to focus on the types of energy that are relevant to the cell. Specifically kinetic energy, which refers to the energy in motion. So molecules are in motion within the cell and they have kinetic energy associated with them. Potential energy, the energy that is stored either within a structure or within a object not being in motion. And chemical energy. This refers to the energy that is stored within the chemical bonds, say, of a glucose molecule. Bioenergetics refers to the study of how an organism can manage those energy resources within itself and also within its environment. And thermodynamics refers to the study of energy transfer within a system, specifically between a system and its surroundings. Within the study of thermodynamics, it's important to understand the concept of entropy. Entropy refers to the disorder or randomness within a system. Metabolism can be referred to as the sum total of an organism's chemical reactions. Within metabolism, we will see there are two main types of pathways that occur, anabolic and catabolic. Anabolic pathways consume energy, and they refer to those reactions that occur when building large molecules out of smaller ones. As we've seen in building up our macromolecules, such as proteins, nucleic acids, lipids, and carbohydrates, we can see that these are being put together from joining together small monomer units. This would be considered an anabolic type of pathway. So the making of macromolecules would consume energy. Catabolic pathways, on the other hand, release energy, which is commonly done by breaking down large molecules into smaller ones. So using the previous example, this would be when we are trying to break apart our macromolecules and digest them, such as what we've seen with the action of the lysosome in the cell. The released energy is usually harvested by the cell in the form of ATP, and this can be used to power all kinds of different reactions within the cell and also to power movement of organelles within the cell as well. An important concept to understand is energy coupling. This is done frequently throughout the cell. This is how anabolic and catabolic pathways relate to each other. Energy coupling states that the energy released from catabolic pathways will be used to drive anabolic pathways. So this means that when the cell is breaking down molecules into smaller ones, it will harvest that energy from that reaction, and it will use it to drive anabolic reactions, such as making different molecules. It is also important to remember the two laws of thermodynamics. The first law of thermodynamics states that the energy in the universe is constant. This means that energy is never created or destroyed, it simply changes form. We can also refer to this law as a law of conservation of energy. That means that energy will be transformed from, say, kinetic energy to potential energy or vice versa. However, no energy will be lost in that conversion. The second law of energy states that the entropy of the universe is increasing. Remember that entropy refers to the disorder in the universe. As a general rule, if a reaction increases entropy, it will occur spontaneously. If it does not increase entropy, it will then require energy input. A good example of this concept is the concept of cleaning your room. In order to clean your room and keep it in an organized state, you would have to invest energy in order to do that. If you stop cleaning your room and stop investing that energy, eventually entropy will take over and your room will eventually become a mess. This is a good example of the second law of thermodynamics. An important concept to understand is Gibbs free energy. This refers to the energy within a reaction, specifically looking at the potential energy, kinetic energy, and the measure of entropy. Gibbs free energy is very useful when looking at the overall change within a reaction. The change in Gibbs free energy can be defined in two ways. First, looking at the Gibbs free energy in the final product minus Gibbs free energy in the initial reactants. And it can also be defined as the change in enthalpy, which refers to the energy stored in the chemical bonds, minus the temperature in kelvins, multiplied by delta S, the change in entropy for that reaction. It is also important to understand what the delta G means and how we can interpret those calculations. So when you have a delta G that is negative in value, this means that free energy is going to be released. Go back to the first equation, delta G equals G final minus G initial. This would mean that if delta G is negative, the final product would have a higher energy value than the reactants. This refers to a spontaneous, favorable, or reaction where no energy is required because energy is actually being released. This would also be equivalent to your catabolic pathways. A positive delta G value, on the other hand, means that free energy is going to be absorbed in that reaction. These reactions are considered to be non-spontaneous, not favorable, and energy is going to be required. So if you have a positive delta G value, this would commonly be referred to as an anabolic type of reaction. An important aspect to also consider is what is spontaneous versus non-spontaneous, considering all of the energy forms in these reactions. When you have a negative delta G value, we can refer to this reaction as being exergonic. Exergonic reactions are considered to be spontaneous, and in general, they gradually move the system towards an equilibrium. Positive delta G reactions can be referred to as endergonic reactions. They're non-spontaneous, require energy from an outside source, and generally tend to move the system away from an equilibrium. Remember the concept of energy coupling. Within the cell, positive delta G reactions will be coupled to negative delta G reactions. Let's take a look at what those reactions look like on a graph. This graph here represents the free energy on the y-axis, which would be referred to as your G value. And on the x-axis, we have the progress of reaction. Usually that means with respect to time. We can see here that the reactants have a very high energy value versus the products, which have a lower energy value. In general, this refers to an exergonic reaction because your reactants have a much higher energy value than your products. Energy would have been released as you form the product. We can see that delta G value on the right part of the graph. Endergonic reactions, on the other hand, require energy and are thus considered to be non-spontaneous. In this graph here, we have the same x and y axis. However, here we can see that the products have a much higher energy value than the reactants. In order to achieve that higher energy state, energy must have been used in that reaction and absorbed in forming the product. We can see here that the delta G value on the right would be greater than 0 and thus positive. How does this concept of Gibbs free energy relate to metabolism? In a chemical reaction, equilibrium is going to be achieved when a forward reaction occurs at the same rate as the reverse reaction. Let's take a look at the diagram below. Here we've got a closed system where we have a high water level in the leftmost container versus a lower water level in the right part of the container. This represents an inequality in energy. So water is going to flow from the high level to the low level. It is going to power the turbine, and this excess energy in this case will be used to light the light bulb. This is representative of a reaction where the delta G is less than 0. You're going to have excess energy that is going to be released in the system, and in this case, the energy is going to be used to light the light bulb. This flow of water or flow of energy is going to occur until an equilibrium is reached, which you can see on the right of this diagram. In this case, the delta G value is 0. The movement of water molecules would be equal on both sides, and there wouldn't be any excess energy, so the light would be out in this instance. This represents your equilibrium state. When your delta G is equal to 0, there's no work being performed. Let's consider we now have an open system. Once again, we have a delta G value of 0. When there's an open system, this water is going to continue to flow. Energy is going to constantly be released. How this relates to metabolism, metabolism takes this concept and we can break down that overall reaction into a series of smaller steps. So overall, these steps are going to be negative in a delta G value, so energy is going to be released in each of these steps. However, because we're using a series of steps, we can now harvest energy and use it at multiple points throughout the reaction. This is equivalent to what occurs during metabolism, where your cell utilizes a series of enzymes and a series of steps to be able to harvest energy at multiple points during the overall reaction.